Last time we started section 8.5, which was equations in a Cartesian coordinate system. We looked at graphing, we looked at finding parallel lines, perpendicular lines, and what we're about to encounter in this next piece of this section is looking at what happens when we compare two lines to one another. So these are called sets of equations, and since we're dealing with lines, they're sets of linear equations. All right, so systems of linear equation. A system of linear equations is a set of equations, usually with more than one variable in each equation. So they've usually got an x and a y in them for the ones we're going to be doing. A solution to that system of equations is an ordered pair that belongs to each of the lines. So what does it mean to belong to the line? Well, it means it's a solution for it. It's on that line. So that is the pair xy is a pair that is common to or satisfies both equations. Graphically, it's the point where the two lines coincide or intersect. So when we're looking for systems of equations, we're looking for places where two lines cross. Okay. There are two ways we're going to discuss on how to find such a solution. There are other ways of finding solutions. One way we're not going to discuss is graphically. So one way is to simply graph both of them and look where they intersect. And if they intersect at a nice whole number, that's sometimes a very nice way to find the solution. And it is often done actually in a middle school type classroom. So it's not that that's not a possibility. Another possible way of doing it, sort of a higher level, and some of you have probably seen this, but maybe not very much, is something called matrices. Matrices is something that can be used, or linear programming. That's kind of above the pay grade of what we're looking at here. We're not talking about that stuff. Okay, so I don't want you to think these are the only ways to do this problems. They're not. These are just the two that are most commonly used. So the first one we're going to look at is substitution method. So these are sort of the steps involved in the substitution method. The first thing is to take one of the equations and solve it for one of the variables. And it is, on purpose, very generic. Either equation, either variable. Totally fine. Second step is to substitute this value into the other equation. And once you've done that, you have an equation with one variable and you solve it. That's step 3, solve that equation. Step number 4 is to take that solution for x or for y and to plug it back into one of the other equations. Okay? And solve for the second variable. Step 5 is one of those things where we don't always require it to be shown, but you should at least visually check, even if it's just in your head, to see that the value works in both equations. Okay, so if you forget that step, it might be okay, but you also might find that you made an error that you could have caught. And then on the 6th one is to either write the solution as an ordered pair, if there's no context to the problem, or to write it with units if there is context to the problem. And we're going to do an example that has context. Okay? So ours is not going to be written as an ordered pair, it's going to be written with units after it. Ready to take a look at one? Awesome. Real life examples of systems of equations are very, very prevalent. So here's an example of one for a movie theater. At a movie theater, a child's ticket costs $5 and an adult ticket costs $8. On Memorial Day, the theater counted 562 audience members, and they made a total of $3,785 in ticket sales. How many child tickets and how many adult tickets were sold? Okay, so the first thing that we need to do is we need to actually figure out what we want to let our variables be, and we get to choose that. So if you want to use just the basic x, y because that's what everybody uses, fabulous. If you want to use a and c because it's adult and children, that's fine too. I had a student once who always liked to use the initials of her name. She did. Anytime she had to create her own equations, she used the initials of her name. So if that's you, that's fine. There are some letters that are not conducive to doing this with. I would recommend you don't use T's and S's. T's look like plus signs for a lot of people, and S's start to look like 5s. These are just not variables that are nice. O would be awful, and so would L. Okay? So use some common sense in what you're doing. But we do need to have something for children's tickets and something for adult tickets. I'll use X and Y for this one, and I'll use the more creative letters of something or else for our next problem. Okay, so X. Now, I don't want you to write down just X as child tickets. That's actually not what it is. What is it? No. What are we asked to find? The number. It's the number of child tickets sold, right? So this is the number of child tickets. The reason I emphasize that is because in our other problem, the variables are actually going to represent the price. Okay, so there's a difference. We know the price on this problem. It's $5. We don't know the number that were sold. And then we'll let our y be the number of adult tickets. So, be clear in what you're defining your variables to be. Make sure that they really are what you say they are. Okay? Now, it tells us two pieces of information that we can use. One that talks about the price that was actually brought in, or the amount that was actually brought in, and one that talks about the number of tickets that were sold. And those two pieces of information, along with the price of the individual tickets, the 5 and the 8, will help us to create two equations. So can somebody give me one of the two equations?
X plus 8y equals the 562. Would you do audience?
Okay, so 5x plus 8y, but it's not equal to the 500 number.
Oh, I thought it said tickets and not. Okay, sorry.
It's equal to 3,785. Yeah. Okay, so this is the equation that talks about price. Okay? So if you have 10 tickets sold, you do 5 times 10, that's $50 in child tickets, right? Okay, so you're just multiplying the price of the ticket 5 times the number of child tickets. The price of the adult ticket 8 times the number of adult tickets. And that equals the total price that was brought in by this theater. That's actually the more difficult of the two equations. What's the other one?
X plus y equals 562.
Right. X plus y equals 562. This is just the number of tickets. Total number of tickets, 562. Total number of tickets is adult tickets plus child tickets. Okay? So setting up our equations, that's not even like one of these steps. This is like step 0, right? You just thought there were 5 steps. There's really like 6 or 7 or 8. I don't know. But this is what we have to do before we start with that, right? We actually have to have the equations we're working with, if there's context. If there's not context, and we'll do another example here in a little bit, then they've already given you the equations and you're good to just start. Okay, so the first step then says that we're supposed to solve one equation for one variable. Make it a good choice. You get to pick. Which equation's easier to work with for solving? The second one, right? Why is the second one easier to work with?
It doesn't have numbers in front of y.
Doesn't have numbers in front of x or y. Okay, so make a choice. I mean, you get to choose, so make it the easier of the choices. So let's take the second equation. Would you like to solve it for x or for y? This is step 1, so I'm going to write it down. X. Okay, Brendan says x, which means he wants to subtract the y to the other side. So he's going to have x equals 562 minus y. That's step 1. Solve one equation for one variable and you get to pick. Step 2 says I'm going to do what?
Substitute the value.
Yeah, I'm going to substitute that. Actually, let me do this for just a second. I'm going to run out of space if I'm not careful. And I didn't leave a blank slide on today's. So let me move this over. Okay, steps 2 is to substitute that value for x into the other equation. The other equation has 5 times x, but x is the same as 562 minus y. So we're replacing x with that value. And then I have plus 8y equals 3,785. Okay, so far so good? Now what?
Needs to distribute the 5.
Yeah, we need to distribute the 5. So we're going to distribute the 5 across here. So the first one, that's easy, is the more difficult of them. What is 5 times 562? 2,810. And then I have 5 times negative y, which is negative 5y, plus 8y equals 3,785. Do you have a question, Lexi? How can I help?
Yeah, why did we, on step 1, why did we go ahead and solve for x and then, like, in step 2, we went back to the x plus y?
We didn't go back to x plus y, we went to the other equation. So in step 1, we used this equation, and we solved it, but then in step 2, we went back up to the other equation
So if
and
you,
used it.
Okay.
if you did it the opposite opposite way? Couldn't you just get x and y from that and plug it into x plus y?
No, because then you'll just get it like 0 equals 0, which won't solve anything for you. Yeah. You have to use both equations or it's not going to actually find a solution. All right, I've got negative 5y plus 8y. That's 3y, right? Okay, what's next? Subtract the 2,810. Okay, so what is that if you take 3,785 minus 2,810? 975. One more step. Divide by 3. Now, this better be a whole number. Why?
Because you can't have half a...
Yeah, this is the number of kids that got tickets to the movie, right? Okay, so think about it logically. If you got a fraction or a decimal here, you would have made a mistake and you need to go back to find it. But if the x actually represented a dollar amount, would it be okay then to get a fraction or a decimal? Sure would. Okay, so if you think about what your x really represents, or your y in this case. What do we get when we divide this? 325. Okay, so this is step 2 is to substitute. Step 3 is to solve. So this was step 3 that we just did. Solved it for y equals 325. Step 4 is to back substitute. It means to take my solution that I just found and find the other variable. I've got 2 equations on the board. Which one's easiest to solve to find x? The second one. And in fact, it's even easier if I use the version of the second one that's on the very bottom left-hand side of my screen. Right? Because it's already solved for x equals. So I know that x equals 562 minus y, so I can do 562 minus the 325. What will that give me? 237. Okay, so step 5 is not really a check step that you have to write down, but it's something that would be wise for you to do. How could we make sure that these numbers work?
Check them in either equation.
Okay, check them, not in either equation, but actually both. So one of them is to add them together, make sure we get 562. So somebody check that for us. Does that work? Olivia's shaking her head yes. Okay. The other equation, what would we do?
Multiply x times 5 and 8 times y.
Okay.
Values to see if we get the...
So whether we write it down or not, we could actually plug it into the other one. So we can do 5 times the 237, right?
Yes.
And 8 times the 325.
So like when she added them together, you could check it that way too, right?
Yeah, but you should check both ways because it's supposed to be a solution to both equations. That's the catch, right? Having a solution to one equation or the other is not helpful if it's not a solution to both. So what is 5 times 237 plus 8 times 325? I hope it's 3,000, whatever we were supposed to get. Yes, Jessica said it is. So we're good to go. So we've checked it. Not only is it a good idea just in general to check it, but it's like equivalent to having the back of the book there with you, right? You can check the answer just like checking the back of the book. You guys check the back of the book. So why wouldn't you check your answer on a problem like that? Right? All right, last step then is to write the solution out in, well, ordered pair if you have that notation, or in this case with units. So let me move this a little bit. Our solution then is to write out what we have. So what do we have?
237 child tickets.
And 325 adult tickets. Okay, and saying the units matters. Because if somebody asks you this question and they say, how many child tickets and how many adult tickets were sold, and you say 237 and 325, then you're leaving it to them to decide which of the order of that, did you say it in the right order that they asked the question in? You know what I'm saying? But if you clarify by using the units, then there's no possible way that you're going to confuse the two answers for each other. Okay, so this is called the substitution method. You guys remember doing this back in, you usually encounter it first in junior high, but definitely in high school. Okay. The second method is called the elimination method. And sometimes I want you to write above the word elimination, I want you to write addition. I have used resources that do not call this the elimination method, they call it the addition method. Okay, so just to be aware. The elimination method does the following. So if necessary, you multiply both equations, potentially both equations, by a suitable number so that one of the variables will be eliminated when you add the equations together. So you maybe multiply, maybe you don't. Maybe you multiply one equation, maybe you multiply both equations. After you've done the multiplication, you add the two equations together. That's why this is sometimes called the addition method. But what happens is that when you add the two equations together, one of the variables gets eliminated. That's why they call it the elimination method. Okay? Once you get that, you're going to have one variable remaining that you can solve the equation for. Step 3 is to back substitute to find the other variable. Check the solution at least mentally. And then write the solution as an ordered pair or with units. So the parts at the end sound alike, right? It's just the way that we solve for the first variable that's different. Okay, if you're not already hungry, you might be now. At a bake sale, Cassandra sells 4 muffins and 6 cookies for a total of $18. Michelle sells 3 muffins and 11 cookies for a total of $20. How much does a muffin cost? How much does a cookie cost? Okay, so this is the one where I was telling you, you could get like a decimal number of a value here and it would be okay, right? Like you could have a cookie that actually costs $1.50. That'd be okay, but you can't have 1.5 children. Promise you can't. Definitely 2. If you've got 1.5, you've got 2. All right, so when we're looking at what we're finding here, we'll use C and M just so that I can show you that it'll be okay if we don't use X and Y. What would C be? The cost of a cookie. Very good. So this is actually a cost. This time we want to write it that way. Cost of a cookie. And M would be the cost of a muffin. Okay, so far so good? All right, we need to create 2 equations. And they're based on these 2 young ladies and how much they sell. So the first one is Cassandra, and she sells 4 muffins and 6 cookies for $18. What kind of an equation is that going to create? What's it going to look like? 4m plus 6c equals 18. Okay, so you take the number of cookies she sold times the cost of the cookie, the number of muffins times the cost of a muffin.
So basically we're going in order.
Yeah. And then we have Michelle. What about Michelle? What is her equation going to look like?
3m plus 11c equals 20.
Okay, everybody good so far? Okay, now, if you just added these equations together, right, added the C's, added the M's, added the dollar amounts, that would be a reasonable equation. It just would be unhelpful. The goal is that when I add the equations together, one of the variables, either the C or the M, goes away. I want it to go away or I won't be able to solve what's left. So when we're looking at this to find a suitable number or 2 suitable numbers, our goal is to either eliminate the M or eliminate the C. And neither one in this case is easier or harder than the other one. Okay? Sometimes there's a very natural choice on which variable to eliminate. Here, not so much. So I'm going to suggest that we just do the very first one and eliminate the M. Okay? One of the letters M has a 4 in front and the other one has a 3. In order to eliminate them, we have to multiply something by them to get them to be the same number. What number are they going to become? 12. And what you've actually found when you did that is something we did in proportional statistical reasoning. That's not true. We do it in number theory. That's where we see this. We do it in number theory, and it's called, say it again, least common multiple. The 12 is the least common multiple of the 2 values. So we're going to multiply the first equation by 3 and the second equation by 4 Almost. We need one of them to be negative, because otherwise, again, they don't add to 0. So pick your favorite. I'm just going to pick the second one to be negative. So this is step 1. We're working on step 1 here, and we're going to create 2 new equations with different numbers. And the number you've multiplied has to be multiplied every term. So they have to be multiplied by the m value, the c value, and the dollar amount that's on the right. So we have 3 times 4m. That whole point was to get the 12m over there. 3 times 6c, which would be 18c. And then I need 3 times 18. What's that? 54. Thank you. Second equation, negative 4 times 3 would be negative 12m. Negative 4 times 11c would be negative 44c. And then negative 4 times 20 would be negative 80. You look confused, Morgan.
Yeah, how'd you get those numbers? I'm so confused.
I'm just multiplying.
Okay.
Like that.
Oh, okay.
You just have to distribute the number through all the terms.
Wait, but how did you get this? Did you add the,
I
like,
haven't added anything. I've just multiplied the number through each equation.
so you did 3 times 6 and negative 4 times 11.
Yep.
And then you added them together?
Not yet, but I'm going to,
Okay, so how'd you get 44 out of that? Because they're 2 separate numbers.
because I multiplied 4 times 11. Right?
But you don't take the first one? Like the 3 times 6?
Okay,
You
this
don't do anything with that?
this equation, that's not what I wanted to do.
That one's not being used.
Oh, yes, it is. This equation turned into that one.
Oh,
Those are the same equation, but one of them's but the second one has multiplied the 3 through it.
okay.
And then this equation is the same as this one with the negative 4 multiplied through.
Oh, okay, so they're, okay.
Are you good?
Yeah, I was just a little confused where those numbers came from.
Okay. Is everybody clear on where the numbers are coming from at this
Yes.
point? Okay. I'm going to take these boxes away because I can't see hardly.
Really make a lot of sense.
All right, but Morgan's right. The next thing we want to do is to add those together, which was our point, right? Our goal is to get them so that when I add them, something goes away. And in fact, that's exactly what happens right here, yeah? Those add to 0. That's our goal. If they don't add to 0 somewhere, either the m's or the c's, then we made a mistake in our multiplication or in the numbers that we chose to multiply by. So these go away. And then I've got 18 and negative 44. What's that? How much? Negative 26c. What about the right-hand side? It is negative 26 as well. What's c going to equal? 1. 1 what? Yeah, it's $1. The cookie is $1. It's not the number of cookies, though. It's the number of dollars for the cookie. Right? $1 for the cookie. All right, that's the cookie, but I also need the price for the muffin. How am I going to get that?
Plugging in the price of the cookie into both of the equations.
Just one is sufficient. We can find one equation with the number plugged in. So just because it doesn't make any difference, I'll just use the first one. 4m, so this is step 3, by the way. 4m plus 6 times c, which is 1, equals 18. So this is 4m plus 6 equals 18. What's next? Subtract my 6. 4m equals 12. Divide by 4. M equals 3. Okay, let's check and make sure it makes sense. How do I do that? This isn't a step you have to write down, but what would you do? Plug it in, and this is where we do the both equations, like you were asking about the both a minute for. So Jamie's right. So we're going to plug it into both equations and make sure it holds and works, right? So
Prove it on our homework?
you don't have to. No, because it actually even talks about in these steps that it says at least mentally. So it's a check step that I think it's really unwise if you don't do it, just for the sake of knowing that you did it right. But it's not something you have to show.
Right.
Okay? All right, so if you plug in C is 1 and M is 3, you would have, I'll show what it would look like just so you have it written down if you'd like. You can show it on your work if you'd like. So 4 times 3 plus 6 times 1. So 4 times 3 is 12, plus 6 times 1 is 6, and sure enough that equals 18, right? And then the other one is 3 times 3 plus 11 times 1. So this is 9 plus 11, which gives me 20. That's exactly what it said it should have gotten me, right? So it works, right? This is the correct solution. How do I write my answer?
$3 per muffin and $1 per cookie.
Okay. So $3 for a muffin. $1 for a cookie.
Does it matter how you write it? Like, can I put muffin costs $3?
That's fine. Sure. But you can't just write down muffin 3, cookies 2. Okay? That you can't do. So, yeah. But yeah, there's some flexibility there. Okay, a couple more things and we're done with this section. The question you might be asking or might have remembered being asked at some point along the way is how many solutions do you have? And we just did 2 examples and we got 1 solution for each of them, right? So one option is that you could have 1 solution. And graphically what that would mean is that you had 2 lines, they intersect, right? They cross somewhere. That's what 1 solution would look like on a graph. The system could have no solutions. And this is actually the notation for no solution. You will also recognize it's a notation for something else you've seen before, empty set. Mathematics is full of problems like this, where we use the same symbol for multiple meanings. Parentheses are probably the worst, but this one means no solution for this context, okay? No solution. Graphically, there's no intersection. Even worse graphically, or even more specifically, is that what this actually gives you is parallel lines. Right? If lines are parallel, they never intersect. Okay? So parallel lines would give you no solution. And then the third option is that you could have infinitely many solutions, which really just means you have the same line written in 2 different ways. Okay? So our last 2 examples are for us to solve. We can use substitution or elimination, either one. They don't indicate which one we have to use. And our goal is to figure out how many solutions, if any, that we have for each system. Okay, it's a system because there's 2 equations. So which method would you like to use for this one? Either one will work fine. Which one? Substitution or elimination? Substitution. Okay, so if we use substitution, there is one variable that I do not want to solve for in one equation. The 2x. I don't want to solve the second equation for x, because I got a 2 in front of it, right? But all of the other 3 are perfectly fine. So which variable would you like to solve in which equation? X on the top. So if I take this equation and I solve it for x, what do I do? Add y to the other side. So x is equal to y plus 1 or 1 plus y, either way. That's step 1. Step 2. What would I do? Plug in. It's a substitution step, right? It's you take the second equation and you plug this in place of the variable you solved for, in this case x. So you have 2 times the quantity y plus 1, and then minus y equals 5. We'll distribute 2y plus 2 minus y equals 5. Now what? What do you want to do, Tiffany?
I don't know, it's not going yet.
So,
Oh, it's not on my screen. Okay, hang on. Okay, what would we like to do for our first step next? And there's a couple things we could do. Okay, what do you want to simplify, Jamie? Okay, so Jamie wants to combine the y's. 2y minus y would give you y. And we still have the plus 2 equals 5.
and then you could subtract the 2.
Right, and then we could subtract the 2. So what does y equal? 3. And all of this was actually step 3, the solving step. Step 4 is to back substitute. So to take y equals 3 and to figure out x. And the nicest place to do that is where we've already solved for x. X is y plus 1. So x is equal to y plus 1, and y is 3. So x is 4. Okay, the check step, right, is to take the 3 and the 4 and see what happens. So if I put it into this first equation, x is 4 and y is 3. 4 minus 3 is 1. That's great. The second one here, x is 3, so that's 2 times 3. Was it 3 or was it 4? Which one was x?
4.
Sorry, x is 4. So x is 4 minus the 3. So what's 2 times 4? 8, and 8 minus 3? 5. So that checks as well. So this actually is the solution. What would I do, or how would I write the answer?
4.
As an ordered pair. And what would it be, Catherine?
4, 3.
4, 3. Why 4, 3 and not 3, 4?
Because x is 4 and x is the first.
Yeah, we always put the x variable first, right? The x value first. So 4 and then 3. Everybody good with that?
So that's where they cross.
If you were to actually graph these two equations, they would cross at the point 4, 3. Okay, since we did this one with substitution, let's do the second one here with elimination. There's something you need to notice before you get started on this one too far in. What do you notice?
They both have numbers.
They're both numbers in front. The y doesn't on the first equation, actually.
Yeah.
I heard something over here. Was that?
We're not lined up.
They aren't lined up. Good job, Lexi. Okay, so in order to work with these, with elimination, they got to be lined up. I mean, the x's have got to be in the same location, the y's in the same location. So the first thing I'm going to do is I'm going to change the second equation so that I put the x first. Because, you know, I mean, it's alphabetical order, right? And then the first equation will stay the same. 2x minus y equals 1. They're lined up. Now I have to find suitable numbers. Numbers that I can multiply one or both equations by so that when I add them together, I get the right thing. Do you notice the signs are already the way I want them to be? Like, let's just try to get rid of the x's. Let's do that. They're opposite signs already, correct? So that's good. What would I need to multiply, and by which equation?
2 by the first equation.
The top equation by 2. Okay, so if I take the top equation and I multiply it by 2, then that top equation, we'll just keep going across my screen this way just for fun. The top equation becomes 4x minus 2y equals 2. The second equation doesn't need to change because it's already got the negative 4x, and then I have plus 2y equals 3. So the x variables, when I add them together now, are going to become nothing, correct? We're going to eliminate each other.
So do the y.
Oh, so does the y. So what is left on the left? Not on the right, the left. 0. Okay, 0 is left. And what's on the right? 5. And does 0 equal 5? No, it does not. So if this happens, right, this means you have no solution. It means that the lines are parallel. Let's say for a moment, just supposing, that instead of getting 0 on the left and 5 on the right, you got 0 on the left and 0 on the right, or 5 on the left and 5 on the right. They actually did match. What would that mean, do you think? They're the same line. It would mean they have infinitely many solutions, because that's a true statement. This one's false. So we have no solution on this one.